Today, we are diving deep into advanced software design patterns. This is really the shortcut you need to be well-informed on writing truly elegant, maintainable code.
It really is. I mean, our sources lay out this incredible roadmap with canonical examples and Python implementations.
Right, and this knowledge is just so valuable for anyone looking to, accelerate their understanding of good software architecture.
Absolutely. Think of these patterns not as optional extras, but as proven solutions to problems that come up again and again. Learning them is the difference between surviving a massive code migration and just drowning in technical debt.
We've got a fantastic stack of research here. It covers a lot of ground. To frame it for you, the sources highlight a few key patterns: the adapter, the facade,
Yeah.
lazy initialization,
Flyweight, abstract factory, composite, and the template patterns.
the whole architectural toolkit, really.
It is, but for today, we're going to zero in on two foundational ones that are, frankly, essential for anyone working in a complex environment. We're talking about the adapter pattern and the facade pattern.
So managing complexity and achieving compatibility.
That's the name of the game.
Okay, let's unpack this, starting with the adapter. I think the core problem this pattern solves is super common.
Oh, extremely. You're trying to interact with existing code. Maybe it's a legacy system or a third-party library, and you have absolutely zero control over its interface.
And your new shiny code just can't talk to it.
They don't speak the same language. That's the critical point. The adapter allows two pre-existing objects to work together even when their interfaces are, fundamentally incompatible.
Like trying to integrate an old system that spits out XML, but your new service only understands JSON.
Exactly that, a classic scenario.
And this is where that tangible analogy comes in, which I always find so helpful for making it stick. The sources compare it to a real-world hardware adapter,
Yeah, the travel adapter. You're in Europe, you've got your North American plug.
and they just don't fit.
Right, so that little plastic adapter you use, it sits physically between those two interfaces. And it's not just passive, it's actively translating, changing the pin layout, maybe even the voltage on the fly.
So in software, the adapter is that translator. It intervenes so you don't have to rewrite the old code or the new code.
Precisely, it lets them communicate.
So let's get into the specifics of how it translates, because it's not just a simple data conversion, is it? What kind of tasks can an adapter actually perform?
Well, the list is surprisingly varied. You've got the obvious one, converting parameters to different formats.
Like changing a date string from one format to another.
Exactly. But it also handles structural changes. An adapter might need to, say, rearrange the order of the arguments that a method expects. Or maybe the method on the old object was renamed, so the adapter just calls the new, differently named method.
And the sources also mention supplying default arguments. That seems like a really clever architectural move.
It is. If your client code only provides 3 pieces of information, but the object it's trying to use needs 5, the adapter can just fill in those last 2 with sensible defaults.
So it fulfills the contract, and the client code stays clean. It doesn't even know there was a gap.
Right. And this whole idea of wrapping an object to change its interface, it does create some confusion. It sounds a lot like another pattern.
The decorator pattern. I think that's where a lot of people get stuck for a minute. If you're wrapping an object, isn't that just a decorator? Where's the sharp line between them?
That's a great question, and it all comes down to intent. What is the goal? A decorator's primary job is to provide the exact same interface it replaces, but add new behavior.
Like logging or caching.
Exactly. It enhances, but it doesn't change the public face. The adapter, on the other hand, has to change the interface. Its entire reason for being is to make 2 incompatible things work together. It's pure translation.
So it's all about structural compatibility, allowing for that plug-and-play capability, especially with vendor APIs or migrating dependencies.
You got it. And if you want to see this in action, the source material points to a really solid Python example out there that shows you exactly how to implement it. It's a great way to solidify the concept.
So we've used the adapter. Our legacy system is now talking to our new service. Everything's compatible. But what if that system we just connected to is itself this sprawling, complicated mess?
You mean 50 interconnected classes, config files everywhere?
Exactly. The interfaces are compatible now, but just figuring out how to use the thing is overwhelming.
And that is the perfect cue to transition to the facade pattern. If the adapter is your translator, the facade is your mission control, your simplified dashboard.
It's also a structural pattern, like the adapter.
It is, but its primary role isn't compatibility. It's abstraction and simplification.
So it provides a clean, high-level interface to something that's really complex under the hood. A huge library, an entire framework.
Yeah, we often frame it as shielding the client code or, the actual human engineer from having to know all the messy, intricate details of the system they're trying to use.
You're hiding the complexity to maximize usability.
Right, you're preventing that information overload the second someone tries to use your system.
And we can really see why a facade is so necessary by looking at a specific example from the sources. It involves generating diagrams with a tool called Plant UML.
Oh, this one is great. The list of setup instructions required just to run the example code it's kind of stunning.
It really proves the point. So the example lives in a Python file, plantimalmain.py. But to run it,
The source lists them out. First, you have to manually install GraphViz, which is a totally separate piece of software.
then you need a Java runtime environment installed on your machine.
Wait, Java. To run a Python script? That
Yeah.
sounds like an engineering hazard just waiting to happen.
It gets worse. You also have to go and download an external plantiml.jar file. And you have to know the exact file path where your diagram source files are.
Wow. So you have external programs, a different language runtime, external files, specific file system knowledge. That's a recipe for chaos.
It's a technical nightmare. If you, as the engineer, had to manage all those steps every single time you wanted to generate one diagram, you just give up. The cognitive load is way too high.
And this is exactly why the facade becomes not just useful, but absolutely essential. It takes all of that complexity, initializing Java, finding the JAR, passing the right file paths, calling GraphViz.
And it hides it all behind one clean, single method. Something simple like diagramfacade.generateML.
Exactly. That one method handles all the messy orchestration behind the scenes. It provides that simplified API and makes a complex system actually usable. It saves you time and prevents that instant overwhelm.
So wrapping up our deep dive here, we can see how these two patterns manage complexity in different but related ways.
Yeah, the adapter is your translator. It lets incompatible interfaces communicate, giving you integration and stability.
And the facade is your simplified control panel. It hides all the messy logistics, preventing technical debt from just crippling the usability of a system.
But remember, these are just two patterns in a much broader field that our sources have opened up. There's a whole toolkit still there for you to explore.
That's a great point.
We really encourage you to continue that journey. Look into lazy initialization, the flyweight pattern, abstract factory, composite, and template. Each one solves a very specific common problem in software engineering.
Okay, so as a final thought for you to mull over, building on what we've learned today,
I like this.
think about just a single app on your phone. Let's say your banking app trying to use the fingerprint sensor. How many adapter patterns must be running right now just to get that app to talk to your phone's unique hardware?
And on the flip side, how many facades are hiding the sheer complexity of the operating system from that same app, preventing the developer from needing to worry about kernel calls and hardware initialization?
It's incredible when you think about it.
It is. The patterns we discussed today, the adapter and facade, they are the silent, constant forces making your digital world both compatible and simple to use. They are, really, the definition of elegant architecture at work.
Now you know how the magic is made. Until next time, keep diving deep.